We're now going to have a look at the simplest homologous series, and they're called the alkanes. We've just had a look that an alkane contains carbons single bonded to other carbons. Alkanes are also only hydrocarbons. So a hydrocarbon is a compound that only contains carbon and hydrogen atoms. So all alkanes are classed as hydrocarbons. Because they only have single bonds, so an alkane can't have a double bond or a triple bond, we can class alkanes as being saturated. So saturated means that we don't have any double or triple bonds present in the molecule. One thing that's worth knowing about alkanes or any homologous series is that they have something called a general formula. So a general formula is an algebraic formula, and what it does is it allows us to calculate the molecular formula if we know how many carbon atoms there are. So for an alkane, the general formula is CnH2n plus 2. So if I apply this to the simplest alkane, which is only going to have one carbon, N is the number of carbons. So if I only have one, it's technically C1, but I don't need to put the 1 in. And the number of hydrogens are 2n plus 2, so 2 times 1, which is 2, plus 2, which is 4, so that's CH4, which is methane, so that's the simplest alkane that we know. So using that general formula, we can work out the molecular formula of any alkane. So let's start having a look at these alkanes in a bit more detail. So we need to know their names, what the formulae for those are, and the different ways that we can represent them. So the first one, as we said, was called methane. It's the simplest alkane. And methane has the molecular formula CH4. So essentially it just has one carbon bonded to 4 hydrogens. This that I've drawn over here, so where I draw out all the atoms and show all of the covalent bonds, this is called the displayed formula. Okay, so this that I've drawn over here is the displayed formula where we show all the atoms and all the bonds between them. Underneath, I'm just going to write the molecular formula. So the molecular formula shows the actual number of atoms of each element present in a compound. So CH4 is the molecular formula. This here is the displayed formula. The name, so you can always find out the name of an alkane based on what it's made up of. So ane, the suffix, so the bit at the end, ane is going to show that we always have an alkane. So all alkanes are going to end in ane. The first part, so the meth or the meth, this is telling us a number of carbon atoms. So meth or meth always means that we've got one carbon atom. The next one in this series is ethane. So again, ends in ane because it's an alkane. Eth represents 2. So that means this one is going to have 2 carbon atoms in the chain. Again, double check that we have 4 bonds around each carbon. And the molecular formula for this, as we can see, is C2H6. Okay, and if we do that if we use the general formula, if we have 2 carbon atoms, it's 2n plus 2 for the number of hydrogens. So 2 times 2 is 4 plus 2 is 6. So that matches the general formula as well. So this is a displayed formula. This is what we call the molecular formula. We can also write something called the structural formula. So the structural formula should always add up to the molecular formula, but essentially it shows a little bit more detail. So what I tend to do is look at the different units that we've got. So over here, if I just kind of split this down the middle, this is a CH3 unit. So the structural formula at the beginning has a CH3 here, and at the end we also have a CH3. Okay, so what I've written out here is called the structural formula, and it shows a little bit more detail in terms of the kind of carbon units that we've got in our molecule. What we can also do is draw something called the skeletal formula. Now, the skeletal formula is a very simplified way of drawing organic molecules. So essentially what we do is we get rid of all the hydrogens. Okay, we don't show any of the hydrogens, and to represent carbons, to represent bonds, we draw a line. Okay, so the bond represents the bond between two carbons. Okay, so this over here is the bond between the two carbons. At the end of any line, okay, if there's no other line coming off of it, we have a CH3 unit. So what what I've drawn here represents an ethane molecule. So at the end over here, we have a carbon, and because we're at the end of a chain, it's a CH3, and we have a bond to the other carbon. So at the end over here, we have a CH3 as well. Okay, if we have two lines meeting, which we're going to show in the next molecules, that means we have a carbon between where those two lines meet, and then we also have hydrogens coming off of them. So a skeletal formula, we don't show any hydrogens, and we don't actually draw any of the carbons or the hydrogens in. We just assume that they are there. So at the end of this, we have a CH3. At the end of that, we have a CH3. It'll make a bit more sense as we do more examples. Okay, the next one in this group is propane. So again, ending in ane because it's an alkane. Prop now represents 3 carbons. So I am going in order. This here is propane. And again, this is the displayed formula. The molecular formula is C3H8. And again, that follows the general formula. In terms of the structural formula, again, looking at the units, we have CH3 here. In the middle, we now have a CH2. And at the end, we have a CH3. So this here is the structural formula for propane. Now, the skeletal formula, we have 3 carbons. So 1, 2, 3. So remember what I said, we don't draw the hydrogens in, or we don't actually draw or write the carbons in. At the end of this, we have a CH3. At the end of this, we have a CH3. Where we have 2 lines meeting, there's a carbon there. And remember, carbon must form 4 bonds, so that means there must be 2 hydrogens coming off it. So this is one bond, this is another bond, so we know there has to be 2 hydrogens coming off of it. So where 2 lines meet, we have a CH2. So this over here is the skeletal formula for propane. I'm going to show a few more. So after propane, which is 3 carbons, we need to have 4 carbons. So the next one is what we call butane. So bute is for 4 in the chain. And again, each carbon must have 4 bonds, like so. The molecular formula is C4H10. The structural formula, there's a few ways we can write this. So we've got a CH3 at the beginning, then a CH2, then another CH2, and then a CH3. So that's one way we could do it. We are allowed to simplify it further. So because we've got 2 lots of CH2s, that can also become CH3. And then I group the CH2s together and put a 2 outside that. And then my final CH3. So both of those would be correct as the structural formula of butane. In terms of the skeletal formula, I've got 4 carbons. So 1, 2, 3, 4. Okay, they should always be drawn at sort of this zigzag sort of angle. Don't do your skeletal formula like, I don't know, like that. It should be this kind of like spread out angle over here. Okay. So again, at the end, we've got a CH3, where 2 lines meet is a CH2, CH2, CH3. Okay. Right, I'm not going to draw the rest of them out, but I am going to give you the names of them. So in terms of the names of the alkanes, if we have 1 carbon, it's called methane. If we have 2 carbons, it's called ethane. If we have 3 carbons, it's called propane. 4 is butane, 5 is pentane, 6 is hexane, 7 is heptane, gonna run out of space, 8 is octane, 9 is nonane, and 10 is decane. And you don't need to go beyond 10, okay? You can only be tested up to 10. So you need to be aware, 1 carbon is meth, 2 is eth, 3 is prop, 4 is but, 5 is pent, 6 is hex, 7 is hept, 8 is oct, 9 is non, and 10 is dec. So for example, if you were asked to draw the skeletal formula of octane, so that'd be 1, 2, 3, 4, 5, 6, 7, 8. So that's the skeletal formula for octane. Okay. Right, let's just quickly cover the kind of bonding in alkanes and how to draw them. So the simplest one, which is methane, you should know how to draw that in a 3D form already, but I will cover that again. So in terms of the bonds, so if you think about the bond between a carbon and a hydrogen, okay, they both have 1 electron to share, so they share their electrons, and essentially it's the orbitals that overlap. Okay, so the orbital here, the s orbital here will overlap with the orbital here, and the electrons, so those 2 electrons that are being shared, can be found anywhere between them. So when the orbitals overlap, they kind of form this cloud of electron density. So over here, this is basically what we call the electron density cloud. So the electrons that are being shared can be found anywhere between carbon and hydrogen. Okay, and when the bond forms between them, so when the bond forms between the carbon and the hydrogen, or the carbon and the carbon, we call this, so kind of a single covalent bond is called a sigma bond. Okay, so sigma spelled like this. That's a symbol we use for sigma. You can write either of those two, sigma bond like that or sigma like that. This is what we call a sigma bond. Okay, so our methane molecule contains 4 sigma bonds. And if you remember, the electron pairs want to be as far away from each other as possible. So that's why they form this tetrahedral formation, which we've already looked at, like so. So it's tetrahedral in shape. These are each sigma bond, so therefore there are 4 sigma bonds here. And the bond angle between all of those is 109.5 degrees. Okay, and it's also worth knowing any single bond that you have, there is free rotation. So we can freely rotate these atoms here. Obviously it's not going to make an effect to this, but as we look at ethane now, you can see it may have an effect in terms of the orientation. So if I draw an ethane molecule, again, it's tetrahedral at each carbon atom. So that means we're going to have 2 in the plane of the board, 1 going coming out and 1 going in. So if you're asked to draw in 3D, this is what you should do. So again, 1 in the plane of the board, 1 coming out, 1 going in, like so. Okay, so it is in 3D. It is still tetrahedral at this carbon, and it's tetrahedral at this carbon. The bond angle is still 109.5 between these bonds over here and over here as well. And as I said, remember, it's worth knowing that there is free rotation. So what I can do is I can essentially just rotate around these. There's free rotation around any single bond. It's also worth noting that the reason that these are all belonging to the same homologous series. So if I do all the first few of the alkane series, so CH4, C2H6, C3H8 and C4H10, if you look at these, the difference between all of them, as you can see, we are adding a CH2. So as we go from one to the next, we are adding a CH2 unit. And if you remember, the definition of a homologous series is that they are similar in chemical reactivity, and each successive member, so the next member, differs by a CH2 unit. So that's showing that the alkanes are all part of the same homologous series here.